Okay, so let's get started. This is chapter 5. And we are learning probability, okay? And chapter 5 is actually entitled Modeling Variation with Probability, okay? Let's break down this title first. What is variation? Okay, yeah, variation is the spread of the data. Yeah, it's the idea that our data is not all the same, right? Everybody is different. Our data is not the same. Our data has spread. And my mantra in life, everybody is different, okay? What works for me may not necessarily work for you. What works for you may not necessarily work for everyone else. So, variation, we've got that. And modeling variation, what does modeling mean? So, well, when you think of modeling, you think of like America's Next Top Model or Runways or things like that. And that's one definition of the word. And the idea behind those models is that there is a product and they are basically demonstrating what that product might look like, and hopefully in an appealing way that makes you want to purchase the product. And in our case, we have we're modeling variation. So we are trying to get an understanding of how our data is different, how our data has spread, and without actually having to gather data, we want to kind of create a model, like a toy model. Think of like a model train or model airplanes or things like that. It's kind of like just kind of a simplified version that we can work with so we can get an understanding of what our data might actually look like. Okay, so in this case we're making a simplified version that will give us a better understanding of the data. Okay, so it's like a airplane simulator. Okay, you can get an idea of how airplanes fly and work without the risk of dying if you mess up. And in this way, if you mess up modeling your variation, there's minimal threat to life, unless you're making policy, and then that could have serious impacts. But in the classroom level, not so dangerous. But we're trying to get an idea of how our data is different, how our data has spread, and we're going to create a simplified version, or we're going to model it using probability. Okay? And when we have probability, okay, we've got to talk about the idea of probability. So what is probability? All right. And you guys are probably already familiar with some concepts of probability. So for example, I'm going to draw, this is a coin with a dude's head on it. All right. Okay. And we can talk about flipping a coin. And we can say, what is the probability that the coin will land heads? All right, so everybody knows this. Probability. Sometimes it's very difficult to write while talking. What is the probability that the coin will land heads. Okay? And so everybody says 50%, okay? Or that's probability expressed as a percentage. In our class, we will probably prefer to write 0.5, okay? But everybody's comfortable with saying the probability that a coin will land heads is 0.5 or 50%, right? Everybody agrees with that so far, okay? But what exactly does it mean? Okay, what does it mean to say that the probability that the coin lands heads is 0.5 or that the probability is 50%, okay? And so some people, you know, and then if I were to ask this question, or if I ask this question, I almost always hear the same answers in that we're talking about the chance, okay? So we have synonyms for the word probability, such as the chance that the coin will land heads or the likelihood. But we are all talking about the same thing. What does it mean for the, when I say the coin has a 50% chance that it lands on heads, or if I say the coin has a 50% likelihood that it lands heads, or the coin has a 50% probability that it lands heads, what am I asking? We're essentially asking the same question with 3 different synonyms. What does that mean? Okay. And it's a little bit tougher, okay, to answer this question. Or does this question even make sense? No, the question doesn't even make sense. You guys just have this inherent definition of probability that, yes?
What's the numerical definition of a certain event?
Yeah, I guess that's a good starting point here. So, or I'm asking, yeah, what does it mean when I say the probability that the coin lands heads is 50%, or if I say the probability that
equally as likely to land heads as it is tails.
Okay, that's specific to 50%. But if I say the probability that it rains tomorrow is 3%, what does that mean? Or if I say the probability that the sun rises tomorrow is 99.9999999%, what are we talking about here? Yeah.
One has a high probability of that.
Yeah, okay, so we're all using the word probability in our definition here, okay? And that's, I feel like, okay, if I keep going, we're probably just going to go in circles here. So I will work this out. The idea here is we're talking about the long-run relative frequency, okay? This is the notion of probability. The probability of an event, okay, whether it's the coin lands heads or the sun rises tomorrow or that it rains tomorrow or that whatever it might be, the long-run probability of an event, the probability of an event is the long-run relative frequency of the event. Okay. What is a relative frequency? Do you guys remember? I guess I don't need this arrow here. The probability of an event is the long-run relative frequency of the event. What is a relative frequency?
When you put it in percent?
Okay, but what are we? Yeah, okay. So when we created a relative frequency table, we put things into percentages. That is correct. But what were we putting into percentages? Not the z-score. The frequency. Okay, so all right. So we turned the frequency into relative frequency by turning it into a percentage. But what was? Okay, so you guys are going back to this idea of a frequency table. All right. Let's just talk about this. Okay, let's say we flipped the coin 10 times. Okay. So we flipped the coin 10 times. And let's say I got heads, tails, 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 heads, heads, tails, heads. How many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9. And what's the last one? Tails. Okay. Does it matter? How many heads did I observe? 4 heads. and tails. So if I made a frequency table, I would have heads 4 and tails 6, right? Okay, so what is my relative frequency of heads? 40%, right? Relative frequency for heads is equal to 0.4. That's okay with everyone? Okay, so that's after 10 flips. What if I did 1,000,000 flips? Okay. Let's do 1,000,000 flips. Well, my frequency table might look something like this. Heads and tails. I'm going to have a lot of heads and a lot of tails. So I'm going to, maybe I have 499,830, and I would have 501,170 or something like that. Okay? So here my relative frequency is going to be 0.49983, right? Is that also okay? This is with 1,000,000 flips. Yes. Good. Okay, so the idea is that as we increase, we do this event in the long run. Okay, so more than 10, more than 1,000,000, more than 1,000,000,000. As we approach infinity, let me just do this. So as, again, let me just write this definition. Probability is the long run relative frequency. Okay. So as we approach an infinite number of repetitions of the event, the relative frequency that we observe is the probability of the event. Okay, so when we're talking about the probability that a coin lands heads, okay, as we repeat flipping a coin, okay, to infinity, okay, we expect the relative frequency to go to 0.5. Okay. So that's what we mean by probability. As you do something close to an infinite number of times, the relative frequency should be the probability. Now, of course, we don't have the luxury of doing anything an infinite number of times. So we have to, the probabilities that we observe in real life may not necessarily ever be the theoretic probabilities, okay? We have what we call empirical probabilities, which are essentially just relative frequencies, and theoretic probabilities. Okay? So empirical means based on evidence, empirical probabilities are basically relative frequencies from actual trials. Okay. So if you flip the coin 10 times,
Does that say as we blank flipping a coin?
as we repeat flipping a coin, it does not say blank. It says, as we repeat flipping a coin to infinity, we expect the relative frequency to go to 0.5. Okay. The empirical probabilities are essentially relative frequencies from actual trials. So we flip a coin 10 times, it lands heads 4 times. Our empirical probability is equal to 0.4. Now this seems silly, but sometimes empirical probabilities are very useful. Okay? On the other hand, we have theoretic probabilities, and let me just talk about both of these. Okay. Theoretic probabilities are calculated using rules, okay, or axioms, using rules or axioms of probability. Okay, and so for flipping a coin, the theoretic probability. Is there a question going on there? Okay. Well, I'm happy to answer questions. The theoretic probability that a coin lands heads is equal to 0.5, and that's based on the rule or assumption that each side of the coin is equally likely, okay? And so that's how we arrive at this theoretic probability. So sometimes, and the rest of this chapter will focus on calculating theoretic probabilities and using them, or, well, I wouldn't say all of it, okay? A large portion of our chapter will depend on theoretic probabilities, okay? But empirical probabilities are useful to us when the math behind theoretic probabilities get really complicated. Okay? Was there a question back there?
Yeah, I was just wanting to make sure you said probabilities are calculated using rules or axioms.
Yeah, rules or axioms. And sorry for the gibberish chicken scratch here, but you know, you're accustomed to writing on paper, and when you write on paper, you can see the trail of the ink. But when you switch to a tablet, you're writing on this, it's like writing with invisible ink, but you can see it on the screen, and there's this.
It's better on this than the chalkboard.
Is it better on this than the chalkboard? Okay, well.
The chalkboard I can see.
Okay, well, I'm glad you think so. So, oh crap, I just did something. Okay. Okay, so we have theoretic probabilities and empirical probabilities. So sometimes, well, you know, for flipping a coin, it would be silly to use empirical probabilities because it's very easy to calculate the probability that a coin lands heads. Okay. But, well, you know, let's say, let's say there was something, a contraption, okay? somebody says, I've got a contraption that will flip coins, and it's designed in such a way that it's going to favor one side of the coin over the other, okay, right? Because if you think about it, why is a coin flip random, okay? And you've got this coin, and you're flipping it up in the air, but if you think about it, and, well, I don't know how you live your life, but is it truly random, right? If we could understand the physics and know exactly how much force went into hitting the coin, went into, I don't know, the air resistance and the weight of the coin and all of this stuff, is it truly random, or is it determined, right? There's... and I would say, a coin flip, based on physics, like if you knew all of these things, you should know how the coin's going to land. It's just all, complicated physics formulas are not even that complicated, but it's all there. And so maybe somebody says, well, I've got a machine that's very precise in the way it launches coins, and in fact that, if you put the heads on top and you flip it, it's going to land heads more often than it lands tails. And you're like, oh, I got to check this out, okay? But he says, well, but I don't know all the rules, and the physics are too complicated to figure out. So how can you check the probability that this machine causes the coin to land heads? Okay. Well, it's going to be too hard to do it the theoretic way. It's going to be too hard to try to figure out all of the rules and the measurements and all of that stuff. So the best thing you're going to do is you're just going to use the contraption to flip coins. You're going to do it thousands of times, and you're going to count how often it lands heads. And then maybe it lands heads more often than it lands tails, and you can get an approximation for the actual probability that the machine produces. So maybe you flip it 1,000 times and it lands heads 600 times, okay? Well, from that, you'd say, okay, or 603 times. You'd say, okay, well, the empirical probability indicates that the probability of it landing heads is around 0.603. Maybe it's a little higher, maybe it's a little lower. But that will allow you to get an estimate without going into the theoretical math there. Does that make sense? Okay, and so sometimes empirical probabilities are very useful. For simplified things and a lot of the examples we cover in class, we're just going to focus on the theoretic probabilities. But we should not forget that empirical probabilities exist. Okay. All right, so let's get into some of the rules of theoretic probabilities. Okay, so we're going to learn some rules for calculating Okay, so first of all, when we talk about events, so we have some event, okay, and we might abbreviate the event with a letter, okay, some event, okay, and this can be abbreviated with a letter. Like A, okay? So we can say A is the event, and then we talk about the probability of the event. And so we will write that as probability of A, or we might just write PR of A, and sometimes we can just write P of A. These are all saying the exact same thing, all right? So these are just three ways to express the probability of the event, okay? We assign numbers or numeric values to the probabilities, not to the events themselves, okay? Always assign numeric values to the probabilities, of probabilities and not the events themselves. Okay, so good to write probability of heads equals 0.5. That's good. Bad to write heads equals 0.5. Because coin landing heads is not 0.5, it's the probability that the coin lands heads is 0.5, okay? So this is, okay, so all probabilities must be between 0 and 1, okay, inclusive, meaning it can equal 0 and it can equal 1. Okay, it can never be bigger than 1 or 100%. It can never be negative. Okay? Are never bigger than 1 or over 100% or negative. Okay? At least in this class. There's some other strange versions of statistics and stuff, maybe, or probabilities, you can have these changes, but in this class, this is always the case. Yes?
Where it says always assign numeric values to the probabilities,
Uh-huh.
let's say and.
Yeah, and not the events themselves.
I'm thinking.
You're making me self-conscious about my penmanship here. Go home, download some second grade worksheets and trace letters. Okay.
Follow dotted line.
Yeah, follow the dotted line. Life is hard. All right, so probabilities must be between 0 and 1. Probabilities are never bigger than 1, and they're never negative. Okay, so sometimes we have in situations, okay, so sometimes we have situations where all simple outcomes have equal probability, okay? Simple outcomes have equal probability. So for example, flipping a coin, heads and tails have equal probability. Rolling a die, all sides have equal probability, or selecting a card from a deck. Card from a shuffled deck. So all of these things should have equal probability, okay? And so we can talk about the probability of certain outcome is equal to the number of events in the outcome divided by total number of events possible. So for example, if we talk about the probability that a coin lands heads, or let's just do coin lands tails, there's only one outcome that counts as coin lands tails, and that's the coin landing tails. And there are two possible outcomes, heads and tails. So that's how we get the probability 1 over 2. Is that okay? If we talk about the probability that a card, a selected card is a heart. Okay. So how many cards are in a total are in a deck?
52.
There's 52 cards total in a deck. How many cards are hearts? 13 hearts. Okay. So our probability is 13 out of 52, which simplifies to 1 out of 4. Okay. Is that okay? So that's the easy part. Good. Move on to the next page. Okay, we have what we call complements of events. Okay, complements spelled with an E, not an I. It's not a nice, friendly thing to say. Complements here are complements of events are when the event does not happen. Okay, is the complement of an event. Complement to an event is the event, or is the occurrence that the event does not happen. Okay, and there are several ways we can write complements. Okay, so if we have some event A, the complement so we have event A. The complement of A is AC or not A, or sometimes A prime, okay, A apostrophe kind of. Okay, the book uses AC, I probably use not A most often. So if we have, if A is equal to coin lands heads, what is a complement? A complement is the coin does not land heads. Which would include every situation where the coin does not land heads. So it could land on its side, it could land, I don't know, land on its side or get eaten by an eagle as midair explodes into a million pieces. Everything where the coin does not land heads is included in a complement. Okay. Now we could say we have a simplified worldview, and we can just say in our simplified worldview, if it doesn't land heads, that means it lands tails. We can do that. Okay. And we just say, and if those things don't happen, if it lands on its side, we just have to ignore that outcome. Pretend that it didn't happen. Okay? So we can simplify the world and say not heads is equal to tails. Okay? But that may not necessarily be the case, right? We often do this for things like sex and gender, right? A lot of times we say there's only two two sexes, male and female, but the world is a little more complicated. But when you fill out a form, you're often forced into the simplified worldview. Okay, and it serves its purposes, you know, because life is complicated, and so sometimes it is useful to simplify things, but we should also recognize that it is a simplified version. Okay, so coin landing heads, you know, heads and tails, it's inconsequential, you know. Determining the sex, maybe more. That was always, you know, when I have a daughter, and I would have this when my wife was pregnant. Why am I sharing this? When my wife was pregnant, I always had this fear that my child would be born with, you know, both sets of privates, and the doctor would force me, because a lot of times the doctor forces you to make a decision, and they go through with this surgery like immediately or like within a very short time, and it's a huge like burden and weight and responsibility, you know, this decision that you make, because that's going to affect the course of this person's life. And that was my great fear. I just thought, don't make this, don't put the weight of that on me. But okay, anyway. Well, anyway, we're talking about probabilities of coin flips and events here. Okay, so anyway, when we talk about, she was born female, and everything seemed normal. I mean, she's a year and a half, so I don't even think she knows what a female or male is. Anyway, that is to be determined. But as far as making a choice, I did not have to do that, so I'm thankful for that. But that's it's a great burden. I don't know how people can handle that. Okay. Anyway,
I have a couple questions.
Yes. Yeah. Good.
What's the third exponent next to A?
Yeah, it's just
Is that an apostrophe?
it's like an apostrophe. It's called a prime symbol. It's kind of like yeah. Technically, so apostrophes look like, if you magnify them, they look like this. They're supposed to. And then this one looks kind of like this. In most fonts, there's not a distinction between the two, but, you know, this is, there is a difference between, I don't know. Any typography experts here? I don't know. What do you call this and what do you call the other one? It doesn't matter. Don't.
Smart quotes.
Smart quotes and dumb quotes. All right. Okay, so it's a dumb apostrophe is what it is there.
And the other question is, why is it called complement?
Why? Okay, because complement comes from the word complete. Okay, so the two things complete the world
So
in that.
assumes the simplified version already?
No, the complement completes the other event in terms of everything that could possibly happen in the world is contained between A and its complement, okay? When you flip a coin, either A happens, or whatever you do, either A happens or its complement happens. There's nothing else possible, okay? So that's why they complete each other. Okay, so anyway, the probability of the complement is equal to 1 minus the probability of the event. Okay? So if the probability of the coin landing heads is 0.5, the complement is 1 minus 0.5. If the probability, you know, if we have B is the event that it rains tomorrow, and we say the probability of B is equal to, I don't know, 5%, then the probability that B does not happen would be equal to what? 1 minus 5%, 95%. So we have that.
Which distinction do you prefer to use? The A over C, the not A, or the A prime?
Ah, it doesn't matter. Okay, tomato, tomato, tomato. No. They're all the same. All right. So you use whatever. I mean, I probably write not A most frequently, but with the C. Okay, let's talk about maybe using a table here. Okay, so we have what we call mutually exclusive events. And mutually exclusive means if one event happens, the other event cannot happen. So when we talk about mutually exclusive events, we're always talking about two events at a time, okay? So if A and B are mutually exclusive, okay? Another word for mutually exclusive is disjoint, okay? If A and B are mutually exclusive, okay, then the probability of A and B happening together is equal to what?
0.
0, okay? If one has happened, the other cannot happen. So, for example, heads and tails are mutually exclusive. If the coin lands heads, it cannot have at the same time landed tails. So probability of heads is 0.5. Probability of tails in our simplified worldview is 0.5. But the probability of heads and tails is equal to 0. What is the probability that the coin lands heads or tails? 1. Okay? So when you flip a coin, this or this happens. The or in statistics is always an and or. Okay? This or both. So if I say, do you like chocolate or vanilla ice cream? You would say yes. Okay? Because that's how we're using the word or. Okay? Not I like chocolate ice cream, or not I like vanilla ice cream. You just say yes. All right. I guess you could say no if you hate ice cream the rest of life, but so and or. That's what we mean, okay? Let's look at, let's make a table here, okay? And so we have something, there's a, can I go to the next slide? Did somebody say wait?
Yes.
Oh, okay,
Yes.
you did. Okay. Can I now I'm going to the next slide. Like it or not. Okay, so in this data we took a survey of 1858 people, and we said we asked what is your political ideology? And we gave them 3 choices, and they could say liberal, moderate, conservative. Okay, and then we say, and then we asked, what political party are you registered, or what is your political party affiliation? Okay, and your choices are Democratic Party, Republican, or other. Okay? Huh? So there are, again, we're simplifying the world into 3 categories here: Democrat, Republican, or other, liberal, moderate, conservative, and, some people can say, fiscal conservative, social liberal, we're just asked just pick one, right? Okay? I know the world is more complicated, but this is the how we did. So what kind of data are we dealing with here? And how many variables do we have? Yeah, we have categorical data. How many variables?
6. 1, 2, 3.
Okay, so remember, in our raw data table, okay, so the data table, how many rows do we have? You guys are breaking my heart. Okay, raw data table, we have 1,858 rows. Why? 1 for each person. Oh, yeah. Okay. And then how many columns? Okay, 2 columns, maybe an identifier, but 2 columns, 1 for each variable, right? And so, for example, our data might start off looking like this. So we have ideology and party. And the first person says, I am liberal and I'm a Democrat. And the next person says, I'm conservative and I'm registered as an other party member. And the third person says, I'm conservative and I'm Republican. And the fourth person says, I'm liberal and I'm a Democrat. Or whatever, okay? We can imagine this going on for how many rows? 1858 people, okay? 1858 rows. All right. So whenever you see data in a summary table, try to imagine what the underlying data looks like. That will, I think, help. Okay, so anyway, we're going to create a summary table. What will my summary table look like? What do I call this thing? So the summary table for this data will be what? No, it's a frequency table, but we have 2 variables, so we call it a 2-way frequency table. Do we remember this? Kind of? I hope. I should put in questions on my quizzes from previous weeks. Haha. Yeah, that's a great, I don't know, idle threat or real thing. Okay. Okay, so we're going to have a party across the top. So we'll have Democrat, Republican, other. And then we will have liberal, moderate, conservative. And these are the numbers. 306, 26, 198, 279, 134, 322. So if no party affiliation would be considered other. 309, 180. Okay, and so if we have the totals, okay, we would have a total of 1,858 people, and I add up the rows and I get 530, 735, 593, and I get 689, 469, and 700. Okay, so let's use this. So we're going to use the summary table to answer a bunch of questions here, okay? All right, is this okay with everyone? Okay. Just going to move this up here. Okay, and after we do this, we'll take a break. All right, so I might ask, what is the probability? Okay, so we're gonna, so I select someone at random. From the pool of 1858 people. Okay, so that means each person I select, or each person in here, has an equal chance of being selected, right? So each person has an equal chance of being selected. Okay, so what if I ask, what is the probability? So if I select someone at random, what is the probability that the person I select is politically moderate? Okay, don't shout your answers out. What about the probability that this person is a Democrat? And let's do probability that someone is Democrat or Republican. So your answers can be expressed as fractions or decimals. Okay, so the answer to moderate would be what? 735 over 1858. Okay, so notice it's very important that I put it as a fraction. Do not say it's 735, because 735 is a number bigger than 1. But 735 divided by 1858 is not. That is 0.3956. Okay, what's the probability that someone is a Democrat? Oh shoot. 689 over 1858. And again, I get a decimal answer there. 689 divided by 1858. And I would write 0.3708. And what is the probability that someone is a Democrat or a Republican?
0.
689 over 1858 plus 469 over 1858. So Yeah, 689 plus 469, that gives me 1158 over 1858. You guys know how to add fractions, right? Some of you have forgotten, but you got to learn. 0.6233. Okay, it's not 0. Why is it not 0? What would, because it says or, okay? If I said, what's the probability that someone I select is Democrat and Republican? The answer to that is 0, okay? Because when you took this survey, you cannot have answered both Democrat and Republican at the same time. Are all of these topics okay so far? Okay. All right. So one thing to note is that, well, actually, let's continue on here. And I know I said we were going to take a break, but it's still related to this table, so I don't feel like I don't think I've lied to you yet. Actually, I never intend to lie to you guys. Let's see. Do you want to save changes? No. Paste. All right. Just a few more questions here related to this table. What if I ask, what's the probability that someone is conservative and a Democrat? What's the probability that someone is conservative and a Democrat? $104 divided by 1858. Okay? Because I'm selecting someone at random. Okay? I select someone at random from the pool of 1,858 people. Okay? So there's 1,858 people total possible, all equally likely of being selected. How many people fit this description, conservative and Democrat? 104 people. So the answer to this question is 104 divided by 1858. Is that okay? Some people brought up some other fractions which would be valid to answers to other questions, and we'll go over those after the break, okay? So the answer to this is 0.0560, okay. Conservative and Democrat, okay? And then let's do one more. What's the probability that someone is conservative or a Democrat? It's not 0. Okay. Yeah, this is a little harder. Okay.
0.37?
Yeah. Okay. All right. Before we get too many crazy answers here, let's talk about, okay, who counts as conservative or Democrat? Do these 306 people count as either conservative or Democrat? Yes, because they're Democrats. They're liberal and Democrats. They count as being conservative or Democrat, okay? Do these 26 people count? No. 198? No. 279? Yes. 134? These people? 322? 104? Yes. 309? Yes. 180? Yes. Okay? These all these 5 cells of people count as being conservative or Democrat. Do we see that? Okay, so my answer could be, I'm just going to use the common denominator on the bottom, could be 306 plus 279 plus 104 plus 309 plus 180. All over what? 1858. So that's one way to do it, okay? Does that work?
Yeah.
Okay, another way is I could use the row and column totals. Okay, I can use 689 and I can use 593. But what would happen if I did that? Yeah, 689 over 1858 plus 593 over 1858, okay? Now if I add these up, you'll notice that the answer, 306 plus 279 plus 104 plus 309 plus 180, that is 1178, okay? 1178 over 1858. But if I check what 689 plus 593 is, it's 1282. So what have I done wrong? I double counted this group, right? Because 104 is included in 689, 104 is also included in 593. So what do I have to do? I just have to subtract off 104, okay? Over 1850. I have to subtract them off once. I don't have to do it twice, just once. Okay, so 1282 minus 104 gives me 1178, and we get the same answer. Is that okay? All right, so when we have probability of A or B, this is equal to the probability of A plus the probability of B minus the probability of A and B. Okay? And if A and B are mutually exclusive, then if A and B are mutually exclusive, what is the probability of A and B? A and B is equal to 0, so then the probability of A or B simplifies to the probability of A plus the probability of B. Okay? Because I'm subtracting off 0, which doesn't change our answer. Okay? So let's take a short break, 10 minutes, and we will continue on after that.